Well, welcome to our first set of notes for this next unit we're going to do. And just a little background here. This is being made in March of 2020, and our nation and the world is in the midst of what we're calling the coronavirus. And so we are out of school. So we're going to be learning in a different way. And in my class, when I do notes, I do them via video, but usually I have some paper notes that we can write on. But we don't have the opportunity to do that here. So some things that'll be a little different for some of you, and depending on who's watching this, you might not be in my class. Maybe this is very normal for you. So I'm going to be doing my notes on just regular paper. So you're going to have to do that too. If you've never done notes on a video before, one of the advantages is you can start and stop the video as you need to. So you notice here, I've already got some things written on the paper. Well, if you need time to write that, you can just stop. And you can't do that in a normal class when the teacher's going on. And just pause the teacher, but you can pause a video. So that's kind of nice. Now, you might be tempted just to blaze through this on a super high speed and just write down what you see on the screen, but you're really missing a lot of the explanation and the context that goes with it. So take your time, watch the video, pause it when necessary, but make sure you're listening and watching and taking notes as you need to, because it's really the whole package there. So it's no different than if you were to just sleep through class and then copy somebody else's notes later. It's not the same as if you were there sort of participating in the lecture the whole time. So when you're ready to go, just go ahead and start this. I'm calling this unit nuclear energy. It's actually a nice connection with some chemistry that you probably did earlier in the year. And this first part here is going to be a review of one of the first things that I did in my class, and probably most of you did in yours as well, and that is to try to understand the structure of atoms, because atoms are what make up all the matter in the universe, and you can't really understand a whole lot about chemistry without understanding what's going on in atoms. Now, the difference with nuclear chemistry is we're not really concerned with the electrons. And the electrons were mostly what we're concerned with when we talk about chemical reactions. But for nuclear energy, we're interested in what's going on inside the nucleus. And so we write things a little bit differently. And so you'll see, for example, some symbols that look like this. You'll have a letter or two, and then a couple of numbers here. I have a 14 in the upper left and a 6 in the lower left. And one of the goals of this first part here is just for you to understand like what we're representing here, because you do see a lot of these symbols when you study nuclear chemistry. So just to kind of briefly describe this symbol here is a letter or letters that we get from the periodic table. Now, you may not have a periodic table in front of you. I found a really great one that I'll show you here, and it's from something called PubChem. So if you just Google PubChem, you will see a link to the periodic table. And what's really cool is you can see different properties. So if you want to see what's a solid, liquid, or gas, or if you forget the names, like in most classes, you'll know that we have the alkali metals here in group 1 and the alkaline earth metals in group 2. Over here we have our metalloids in this sort of stair-step line. And we have some nonmetals here. We have what's called the noble gases. And those are really kind of familiar names if you do a lot of chemistry. So what I want to look at here is the atomic mass. So we'll flip back and forth to that as necessary. So this is a symbol that comes from the periodic table. You might recognize that as carbon. This number up here is called the mass number for this particular atom of carbon. And this right here is what we're going to usually refer to as the charge of this particular atom. So in nuclear chemistry, it's these two numbers that are most important in understanding what's going on. So let's back up a step and talk about what we call the subatomic particles. The key roots here of these words, sub meaning kind of under, and atomic. So these are the particles that make every atom. And there are 3 of them. There are the protons and the neutrons. And I'm going to star those 2 because those are the 2 that live inside the nucleus of an atom. And then the third one, the electrons, again, those are the things we were most interested in when we did regular chemistry stuff. like does one atom bond to another atom? It all depends on how many electrons, in particular the outer electrons, these atoms have. But these are going to kind of be sort of on the sidelines for most of the nuclear chemistry stuff. Okay, so for each one, we're going to want to know its mass number and its charge. These are important characteristics of each of these subatomic particles. The protons and the neutrons are really the only particles that have any appreciable mass. So we assign them a mass number of 1 for each of them, almost identical in mass. But electrons are so tiny, they're about 1/2000th the mass of either of the others. So we assign those a mass of 0. And then another important characteristic is the charge. Hard to describe what charge is, but it is a property you're going to need to know. So protons and electrons are the two charged particles. Protons are a +1, electrons are a -1. Neutrons are neutral, which is why they get their name neutrons. So now back to this symbol. So when we write the symbol or something, here's just sort of a generic format for it. Okay, this will be the symbol from the periodic table. And there is no element X. I'm just using this as kind of an example. And then, as I said before, this number up here, it was 14 up here, but for every symbol, this will just be the total mass inside the nucleus, the mass number. That's every proton and every neutron, the total of those two. And then the charge of the nucleus goes down here in the lower left. Okay, so we have a mass number and a charge, and then we have whatever symbol goes with that particular element. Okay, so let's look at a few examples of these, and we can kind of decipher what's inside the nucleus based on what symbol we see, or vice versa. Based on what's in the nucleus, we can write a symbol for it. So let's look at a few examples of those. Okay, for example number 1, let's describe a carbon atom with 8 neutrons. Now it turns out carbon atoms can have different numbers of neutrons. It's what makes one carbon atom different from another. We call those isotopes, and I'll describe that a little bit later. So on the periodic table, if you find carbon, you will see its symbol C. And then we need the mass number up here. That's all the protons and all the neutrons added together. Well, I told you how many neutrons are in it. There's 8. But how many protons are in a carbon atom? If we go back to the periodic table, here again you're going to want to have one with you. I want to remind you that the atomic number is the number of protons for every atom. So if we can find carbon here, and we see its atomic number is 6, and here's a little guide to what these numbers are. The atomic number is 6. It means it has 6 protons. So there's your proton number. So we have to add that to the neutron number. So that's where we get the 14. And then down here, the charge number, you just count all of the positive charges that are inside the nucleus, and that is each proton, and that's a 6. So this is the example that I had used earlier. Okay, so we call that carbon 14. We usually refer to these isotopes by their name and then their mass number, carbon 14 in this case. Okay, so just to remind you why we're using 14, it's because 6 protons plus 8 neutrons is the mass number. And why are we using 6? Because 6 protons in carbon, every carbon. Okay? So there's an example. So let me show you another isotope of carbon. We'll call this example number 2. This will be carbon with only 6 neutrons. Okay, so there's not a lot that's different here. Because it's carbon, we still use C, and every carbon atom is atomic number 6 and therefore has 6 protons. So that's the only charge that we have in this. Remember, we're kind of ignoring the electrons when we write these symbols for the nucleus. But now the mass number is going to be different because we still have a mass for each proton. That's 6 of those, but we only have 6 neutrons this time. So that's 12. Okay, so this will be called carbon 12. It's the most plentiful kind of carbon that we have. There's a little bit of carbon 14 later. There's going to be a little section in one of the parts later on in this unit where we'll talk about how important carbon 14 is, and you may have heard of that before. All right? So let's kind of twist it around a little bit for our third example. For example number 3, we'll say, what is in the nucleus of, and then here's a symbol. So it's the letter K, 40 in the upper left and 19 in the lower left. Okay? So every nucleus has protons or neutrons in it. How many of each? Always start with this lower left number here, because that 19 tells you the number of protons. How else could you figure out the number of protons? Do you know this? If you go back to the periodic table, here's potassium over here, and its atomic number 19 tells you the number of protons. So you might think, why do we even need to have that number there? And there are times where it's important to have that. It won't be clear now. But we know we have 19 protons. And what about this 40? A common mistake is to say there's 40 neutrons. But remember, this mass is the total of the protons plus the neutrons. So the question is, 19 protons plus how many neutrons is going to make 40? Ends up being a little subtraction problem. 21 neutrons. Okay? And again, what I did here was I did 40 minus 19 equals 21. Okay? So we're kind of working backwards there. How's that look? Okay, for our last example here, and you don't need to wait on me if you can do these on your own, we'll ask this: how many neutrons are in 3 isotopes of barium? Okay, so isotopes of barium, that means they're all barium atoms, but they have different numbers of neutrons. So maybe one is barium 137, and one is barium 138, and one is barium 139. So there are the 3 symbols for them. Notice because they're barium, they all have 56 protons, and so we put that in the lower left. But the mass numbers are 137, 138, and 139. So do you remember how to find the neutrons? It's the same way we did it up here for this potassium atom. If we know the total mass of this barium atom is 137, and 56 of that comes from the protons, the remainder comes from the neutrons. Okay, so 137 minus 56 means 81 neutrons in that particular isotope. And what do you notice about this one? See how its mass number is just one more than this one up here? That means we don't even need to really do that subtraction. We just know there must be one more neutron in there because there's the same number of protons. And this one down here, again, is one higher than that. So this has 83 neutrons. All right, so 3 isotopes, different numbers of neutrons, but we're talking about the same atom. And again, that's really important when we're doing nuclear chemistry. So we've gone on here almost 15 minutes. Hopefully, if this was a bit much for you to sit and watch and take notes straight through, you figured out how you can take a break, maybe go walk around a little bit, go get a drink of water, get some exercise, come back, watch it again if necessary. That's the name of the game when you're doing some of this video note-taking. So that's a good start for now. And just go back and do the next task that's on your list. Hopefully it goes well. Reach out to your teacher for help if you need it. Okay? But we got a good start. Thanks for watching.